Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Right, good day everyone. Last time we started talking about bivariate normals, which were a special case of multivariate normal we'll get to later, but it's worth understanding the bivariate case in some detail. So the point is, it's very easy to put together some bivariate normals, like some relations between two random variables, both of which are normal and which seem to vary together in a normal way. And I gave you one example of a way to do that. You could start with, well, first of all, you could start with two independent standard normals and just consider them jointly, Z and W, and if they're independent, you multiply the densities. The non-independent case, you have to do a marginal density times condition. Remember, joint equals marginal times conditional. And so the easiest way to do that was in the case where you thought of one normal variable being correlated with another one, but also with some extra noise. So here I imagined x and w to be both standard normal. N01 is my notation for standard normal. And I imagine w to be independent of x. So you imagine w here to represent some noise. I start with kind of a signal, that's the x. I add on some linear function of the signal plus some amount of noise. And I've allowed it to have, some scaling times the noise. It doesn't have to be noise, it's variance 1. So the variance of the noise here will be c squared. The variance of the signal will be a squared. I can tell you straight away in this calculation that the variance of y is equal to a squared plus c squared. Does anyone remember y? Y is obtained by combining the signal and the noise. Why can I add variances? The magic word is independence. Yeah. So you're allowed to add the variances of the variance of a sum of variables is the sum of the variances, so long as the variables are independent. If they're not independent, then there might be some other relationship. And it's worth at that point, this is because ax plus b, the signal term, is independent of the noise term, cw. That's because these are just linear functions of the x and w, which are independent. So anyway, you have y, which is a linear combination of those two. And the fact that it's linear, not just any odd function, turns out to be important. It's not a joint normal if it's not a linear function of one variable plus another. So to get the joint density, you do it this way. And the exact formula here ends up not being very important, except for the fact that it is e to the minus something that is only quadratic terms, so only y squared, x squared, and you're also allowed to have some xy terms, and the constant terms also shifted a little bit. So terms of degree at most 2 in x and y. So that, whenever that happens, you have a bivariate normal. So let's go on and now talk about, in this example, I don't even want to simplify the, maybe I'll simplify the density. Why not? Okay, so that's something over square root 2 pi c. Yeah, sorry. So to reiterate, I started this way. I put together the joint density by marginal times conditional. Square root 2 pi c is on the bottom, and on the numerator I have e to the minus 1/2 x squared minus 1/2. Yeah, it's a complicated thing, but I will. Okay, I'm going to simplify my life by imagining b to be equal to 0 from here on. That might seem like a big simplification. It's not really, because it's just a shift of, shifting y by a constant. So in order to have everything mean 0, I'll just assume b is 0 and then x also has mean 0. So then all I'm getting is minus 1/2 y squared minus 1/2 a squared x squared, and then I get the plus 2axy term with a 1/2 there. So that will be plus a x y. So you can and there's a c squared. All of those things have a c squared on the denominator. Maybe I better put that just y squared over c squared, a squared x squared divided by c squared, and axy divided by c squared. Okay, so that's a slightly complicated formula. Why am I going through this? Because I want to deduce the formula in terms of the covariance and the correlation. As we mentioned before, the covariance of two variables, a and b, as we call, is the expected value of a minus expected a times b minus expected b. Now, in this case, we're having so-called centered variables that all have mean 0. So that will be the same as expected value of xy in this context. And I want to, another formula, since I was just talking about the variance of a sum, it's worth remembering that although in the most simple case where they're independent, you can just say that's variance of a plus variance of b. If you simply expand out the quadratic form that you have here, a squared plus b squared plus 2ab effectively, what you get here is plus 2 times the covariance of ab. Often written covariance of ab. So this is a general aside about covariance. So now let's get back to covariance in the context of bivariate normal. Question. For this bivariate normal, and I'll remind you of the definition, x and w are, I guess you could say they're IID normal 0, 1, and y is equal to ax plus cw. I'll remind you that in this context, I consider bivariate normal of x and y. The w is considered noise and is not interesting of itself. It's only interesting in how it affects y. So to do that, we want to calculate the covariance of x with y. That's one thing that's interesting. Well, there are a number of things that are interesting. The variance of x is very easy. It's 1 by definition. We also want to do the covariance of x and y. That's equal to covariance of x with ax plus cw. Now, what can anyone suggest that I do with this calculation on the right? I have x with a linear combination. Sorry, you were about to say? There's a good algebra that should be done with covariance. It follows straight from that definition that covariance is called a bilinear operator. It's linear in A and linear in B. So I'll just say covariance of lambda 1 A1 plus lambda 2 B A2 with B. The bilinearity says that it will be lambda 1 times the covariance of A1 with B plus lambda 2 covariance of A2 with B. That's assuming the lambdas are constants. That's what bilinearity means. Bilinearity linearity is the following statement. Okay? And just reminding you that this is, what that is the definition of covariance. The bilinearity of covariance is quite important. Now, I did bilinearity in the first variable, but of course, covariance AB is the same as covariance BA, so it's also bilinear in the second variable. So if we get back to the application of that bilinearity here, can someone tell me what I should write? Expanding it up. X with X, and what's the coefficient of that one? A, yep. So the coefficient of A comes out the front, and the same with the second term. Yeah, C covariance of X with W. Thank you. So always the coefficient comes out the front, and you break it up as a sum according to the term. The difference would be the same. So would be a minus sign. That's covariance. And now covariance of X with X, that's A times the variance of X, of course, plus C times. Now covariance of two variables that are independent is 0. If you're wondering why that's true, when A is independent, the same is true of the centered versions. This is a centered version of A, and that is a centered version of B. So that centered version and that centered version are independent, and therefore the covariance is the product 0 times 0. So because 0, and this right one is because X is independent of those. Okay? So that's just A times 1 plus C times 0, so it's A. Very simple formula for the covariance. There is another thing that we often talk about, the correlation coefficient with X and Y, because we need that to evaluate it in a unit-independent fashion. The covariance carries the units of X times the units of Y. It's a product, kind of. It's like an inner product. Whereas this is a dimensionless quantity, which is more like the cosine of an angle. And in fact, in n-dimensional space, the correlation coefficient is the best thought of as the cosine of the angle between the two vectors. So if the cosine is 1, then they're exactly the same. If the cosine is -1, then they're exactly opposite. And otherwise, they're somewhere in between. So the correlation coefficient I have to calculate. To do that, I need the variance of Y, which, to reiterate, is A squared plus C squared. We saw that a little moment ago. So this is going to be the covariance of X with Y divided by the standard deviation of X times standard deviation of Y. So there's 1 in one case, and square root A squared plus C squared. So A divided by square root A squared plus C squared. Okay. Now this correlation coefficient, just as a standard letter, is often called rho. Good letter for it. And if you're doing a sampled version of it, it's often called R. So rho is the Greek letter for R. But because this is the theoretical value, not the sampled value, I'm using the Greek letter rho. So covariance divided by product of standard deviations. Now, here's what I really want to do. I want to write down the density of a bivariate normal that has a very standardized form of so this is going to be the probability density function of x, y, where we already know that x is, so far it has just been calculations involving the setup we already had. I'm now going to find the density where I'm going to make an additional assumption. Instead of n, x is normal 0, 1. I already assumed that the white noise was normal 0, 1. Now I'm going to assume y is normal 0, 1. And if they were independent, that would be easy. I would already know how to do that. That would be this formula here. But because they're not independent, I want to do a case where covariance of x, y equals rho. And I should say, as one more condition, the x, y is bivariate normal. Okay. I haven't given a full definition of multivariate normal or bivariate normal yet, but you can take it as one definition of it would be that each variable is obtained by a linear combination of the other variables plus an independent noise, and in some linear combination. That linearity is quite important because I'll show you later there are ways to get marginally normal variables. So this is in case you forgot the terminology. These are the marginals are normal. It's possible to have Martin's normal and indeed particular covariances, but if it's not bivariate normal, then it might not have the following density. In fact, it might not even have a density of it. So the bivariate normality of it, which you can take to be something to do with this construction, is quite important. So, but before we go on to those subtleties, I want to give you what that density is obtained. I just need to get a particular value of rho by setting, you see there's an additional condition. I already set y to be centered by setting b to be, I set the coefficient b to be 0, so y has mean 0, but I haven't yet insisted that y has variance 1. So y has to have variance 1, and we know that variance of y is a squared plus c squared. Yep. And also, I still need, rho is this given value, which is correlation of x and y, and that is, as we said, a divided by square root a squared plus c squared. But of course, 1 equals a squared plus c squared. So that rho equals a, in other words. And the key fact we now draw from this is that c, in order to get this working correctly, I should choose c to be the square root of 1 minus, how do I get rho? Well, c squared plus rho squared equals 1, so c equals square root 1 minus rho squared. Okay? So the c that I choose will always be positive, and a will always be the value rho. And I'll remind you that I can allow any value of rho that is in -1 to 1. And although I'm just going to not allow the end points of that, because the key word here is density. Turns out if you have the end points, rho equals 1 or rho equals -1, it doesn't have a density. It's one of those degenerate distributions that lies along the line. So let's restrict to square root between -1 and 1, and then c will be non-zero. Okay, so let us then use that to find the density. We already have the expression for the density. Fx comma y of xy is equal to, copying from before, e to the -1/2 x squared minus 1/2. Unfortunately, all these c squareds are going to survive. So c squared is 1 minus rho squared. Okay? And I'll have y squared, a squared, x squared. So that's y squared plus a is the same as rho, so rho squared x squared, minus 2 rho x 1. If you're wondering why this was -2 and that one was +1, it's just a matter of fact of whether I took the -1/2 as a common factor or not. Okay, and then the denominator, once I know that that's for density across the whole real plane, what the denominator is fixed by the fact that the integral of the density has to be 1. But nevertheless, we can find the exact value by just putting in square root 2 pi c. So square root. And there was actually, I'm sorry that there was a typo in this earlier bit, because there was a square root 2 pi times square root 2 pi c. So on the denominator, it's actually 2 pi c, because it's in two dimensions. You have not square root 2 pi c, you just have 2 pi c. And in this context, c is square root 1 minus rho squared. Okay. Conclusion, I will be able to make another simplification of this, e to the -1/2. Let's keep the 1/2 as a common factor. The great thing about, I even want to put everything on a denominator of 1 minus rho squared. Okay? Oh, there's of course e to the power. The denominator will stay the same, square root 2 pi 1 minus rho squared. That's the constant term out the front. This exponential is e to the -1/2. You see that x squared gets a 1 minus rho squared, which cancels with the plus rho squared x squared. So it's actually quite a nice simple formula. X squared plus y squared minus 2 rho x 1. Okay, so that is the formula for a bivariate normal. And any bivariate normal, once you do the following things, can be reduced to that simplified form. So this is, just a reminder, this is x normal 0, 1. Y normal 0, 1. not independent, because that would be correlation rho equals 0. This is the case where correlation between x and y is the fixed value rho. Okay, so that is one special form of bivariate normal, but which characterizes, which includes all correlations. Now I'm just going to draw a few cartoons of what this looks like. Always on the x-axis, where I shouldn't say we're always between -1 and 1, where I'm going to put in, -1, 1, -1, 1. So, 95% of the time you're between -1.96 and 1.96 for a normal. So for rho equals, let's do, I'm actually going to do a whole lot of drawings on the same diagram just so you can see how it varies, and they'll be sketches. If you want to see it more precisely, it's quite easy to simulate in R. I'll let you figure out how to do that if you like. So for the standard normal, it will look, the standard joint normal, it'll sort of look roughly like this, more dense towards the center and slightly less dense towards. So I'm drawing the density by sketching a little bit, but the density is higher in the center. It's radially symmetric and it goes outwards. So that would be the case rho equals 0, which is e to the minus a half x squared plus y squared. So just a mountain that goes downwards from the center. And of course it has lower, it can't even go further. Now, so that would be the rho equals 0 case. Okay? Now, the rho equals 1/2 case, let's say, that has a positive correlation. The marginal distributions are still the same, so, but the actual relation between them starts to look a bit different. So this is what rho equals 1/2 would look like. So, and I don't claim it's absolutely accurate, but it's got the correct shape. So it's higher in the middle, it's lower in the edge. The marginal distributions are the same. So if you took up the integral of the joint density along each horizontal line, it's the same as for the blue. If you took the integral along each vertical line, it's the same as for the blue. And yet there's a lot more confounding, well, there's a lot more positive correlation between them. And then you can tend it all the way up to rho equals 1. I'll just say rho tending to 1 in this funny blocky pen. As rho tends to 1, this gets more and more just like a normal lying on a single line. So, and then it's of course much more likely to be in the center there, and then less likely. So rho equals 1 lies exactly on that line. That's not even jointly continuous. It is a joint distribution when rho equals 1, but it's not jointly continuous because that would mean that a jointly continuous thing has 0 probability of lying in a 0 area line, whereas this would always lie on the line. So that's what happens when rho tends to 1. And likewise, when rho tends to -1, you'd expect it to look a bit like this. Okay, if you just imagine sort of, very occasionally it'll be out there, but by far the majority of the time it would be in the center. So that would be the case rho tends to -1. Okay? And then finally, there is, so rho equals, maybe I don't have that many pens, so you can imagine what rho equals -1/2 would look like. It would just be the mirror image of that. All of those are encapsulated within this formula that we've got here. The general formula for the density function, PDF, which is, it went without saying, but I mean the joint PDF of bivariate normal. So they're going to be x and y, but now I'm going to say, let's say mu x sigma squared x. Y is normal mu y sigma squared y. And the correlation coefficient is always important. I'm going to call that rho. So there's 5 pieces of information to understand the general bivariate normal: the mean of x, the mean of y, the variance of x, the variance of y, and the correlation coefficient. So if, for instance, you substituted the correlation coefficient with the covariance, which is rho times sigma x times sigma y, that would be an equivalent piece of information. But in any case, you need 5 real pieces of information. So it is obtained by shifting and scaling. And I did emphasize this before in the one-dimensional case. I think it's not too hard to see how it works. And besides which, we'll be talking about transformations more generally later. But it shouldn't be any surprise that the density xy of xy. How do I get it from what I had over there? Well, the denominator is 2 pi square root 1 minus rho squared. But I have to multiply by something. If you imagine sigma x is 2 instead of 1. That means the x-coordinate has been stretched out by a factor of 2. That means the density must correspondingly go down by a factor of 2. Of course, it has to integrate for 1. So I have to divide by sigma x, whatever that was, because the density goes down by the stretch factor. And similarly, the y has been stretched out by a factor of sigma y. And then finally, I just have to do, if you don't mind, I'll write x rather than e to the. X is just another way of writing e to the. That way I have more space. X of, once again, minus a half. If you don't like the 1/2, it can be, amalgamated with the other parameters, but this is just the most standard way to do it. And then, in fact, I'm even going to put the 1 minus rho squared here, because everything else. So the 1/2, 1 minus rho squared remains the same. And then inside the brackets, I have to do the shifting and scaling in the relevant fashion. So over here, I had x. That has been shifted, and that was a standardized x. So to get from the non-standardized x to standard coordinates, I have to subtract the mean, then divide by the standard deviation. So I do x minus mu x divided by sigma x. Okay, so all that squared. Plus the same thing for y. Y minus mu y divided by sigma y, all squared. Okay? And then I have to put in the same term, minus 2 rho, products of those two things. So x minus mu x, y minus mu y. Each divided by its corresponding standard deviation, sigma x, sigma y. So that is the most general, that includes every two-dimensional bivariate normal, with the arguable exception of the case where rho equals 1 or minus 1, because then you're dividing by 0. So the degenerate cases don't actually have a density, but morally, if they did have a density, it would be this. In reality, what the degenerate cases have, which I did in dotted lines here, they have a density, but only with respect to the line that they lie on, not with respect to the whole space. So that's not a joint density, that's just a one-dimensional density. Okay, so we've done enough on bivariate normal for now. You'll be sad to hear that in higher dimensions it gets even more complicated, so much so that I won't write a formula like that. We may... You're probably getting the sense that this all has a lot to do with matrix algebra and linear algebra, and it does. And so the best way to write it in higher dimensions is to understand the linear transformation point of view for it. But bivariate normal is important enough that it's worth writing down that way. Okay, let's go on and let's talk about transformations of random variables. Okay. And for the moment, we'll be going back. So I think this is called chapter 6 in the book. But there's an argument that the division into transformation versus general properties of random variables is a bit artificial, because a lot of things that we want to know we will do via these transformations. And one of these that we've already done, so you'll see that if y equals f of x, and so back to 1D for now, so one-dimensional for now. We'll do two-dimensional in a moment. But univariate random variables, y equals f of x, and this is just some function. I didn't mean to suggest that's the density. Sorry, let me change my letter to be a g, just in case anyone thought it was a density. It's just an arbitrary function. Then the distributions of x and y are related, quite obviously. If you know the distribution of x, then in principle you know the distribution of y. You know the chance of lying in every set on the plane, on the line. But to be more practical, it can be a bit hard to see exactly, the probability that, to be more precise about it, you could say the probability that y lies in I, we're always talking about an interval I, is equal to the probability that x lies in G inverse of y. If you're wondering what G inverse, this is called the pre-image or inverse image. If you don't know what that means, then you can look it up. It's a fairly standard notion. Just one thing to note is that this pre-image doesn't require g to be a one-to-one function to be defined. I'm not saying that g has an inverse function. I'm just saying that no matter what function it is, g inverse of y is just the set of all points that land and that, yeah, I, thank you for the correction. G inverse of I, yes, is just the set of all points that land in the interval I. Yep. So that's the relationship. But often that can be more, what we really want is a relationship between the PDFs, because I've often said that the density function is a more useful relationship than the interval notation or even the CDF. So there are a number of ways of deducing the, I'll just put them all together. Okay, let's say PDF of y from the PDF of x, if they exist. Now, they don't always exist, and there's even some cases where x has a density, but y doesn't. Can anyone, this is kind of a paradoxical thing, you imagine x to be some random variable. Say x has a density, x could even be normal. Can anyone think of some function of x so that the result will not even be a continuous random variable? It's kind of a trivial thing you can do. Like I take every point on the real line here. If I want it not to have a density, one way to do it is to sort of destroy the fact that it's nicely distributed over the real line, just smush it all together. So one thing would be equals constant. Okay? That's an example. So while this is not the typical case, if you did g of anything equals constant, then all of a sudden you would have turned a continuous random variable into a discrete random variable. It would always lie at the point constant. So just to show you that bad things can happen. So that's why I've got the word if they exist. Even if x exists, if you pick the wrong function, then it might no longer be continuous. And a worse case from that is that if you might like to consider the case where g is a function with the following graph. Like it might not be the constant function, but it might just be something that's sort of constant for a bit of time. If your function is constant for a bit of time, then there's going to be a positive probability of lying at that point. So the point is, there's only certain functions g for which this will necessarily give you a fully continuous image y. But I can give a condition for that in one moment. So first of all, I'll just say CDF method. This is not really new because I already did one example of this. So what is the CDF method? It's because it uses two facts that we already know. Which would be, I'd say A, which is relate the CDF of y to CDF of x. And that is not always simple. It's simple in the case where g is an increasing function or a decreasing function. Okay, so fy of, the chance of being below y is f x of, let's say, g inverse of y if g is increasing. So if g is increasing. Because this is the probability that y is less than or equal to y, little y, and that is the probability that x is less than or equal to g inverse of y. So that kind of makes sense. And it's actually going to be the other way around if x is decreasing. And you might want to assume g is continuous to not worry about the endpoints here. So fy of y is going to be 1 minus fx of g inverse of y if g is decreasing. Okay. Just to avoid any problems, I'll assume that these are continuous functions without jumps. If there were jumps, you might have to worry a little bit about less than or equal to versus less than. So I can't give a comprehensive answer to how you do this because there are ... other if G is more complex, or I'll say complicated, not a complex function. Okay. So sometimes you just have to, use your nous to find a relationship between fy and fx, and then B, differentiate using fx prime of x is, well, let's say it this way, fy prime of y is equal to little f y prime. So both of these things were known before, and we even did an example of this. We did an example that fits into this other category. Can anyone remember what that example was? We actually did it for normal, because we wanted to understand what the square of a standard normal looked like. I did that in the context of talking about gamma distributions. So example, which was already covered, but I'll reiterate since it's a perfect spitting image of this method, is that x is going to be normal 0, 1 in this example. Y is defined in this case to be, well, okay, a function of x, which is x squared. Okay, so concrete, very concrete. And how does that behave? Part A is to relate fy to fx. Relate fy to fx, and I'm going to do that by fy. Y. Now, this, I'm only really concerned with this for y greater than or equal to 0. I couldn't care less about the chance of y being less than or equal to a negative number because I know it's 0. So that is equal to probability that, so just use common sense in doing this. And in terms of x, what are the bounds on x? Root y, certainly, but there's another one. Minus root y. If it were to the wrong side of minus root y, then the square would actually be larger. So the squaring is the obvious example, but any quadratic function would yield to the same method. There might be exponential functions involved, there might be other functions. If it were cubic and higher, then there's real problems in finding the roots of the cubic, as you'd know. So any cubic other than just x cubed is an easy one because you can just take cube root. So some other polynomials you may be able to deal with, but the general cubic, the general higher polynomial will be too complicated to do by this method. And that's why luckily we have other methods than the CDF method, although they are related. So let's go on. And the key thing to do is, in the context of a continuous distribution, I don't care about equals versus not equals. So this is fx of square root y minus fx of minus square root y, right? I take chance of being less than or equal to here and subtract the ones that are too small. And so f, little f, y equals big F, y prime, y. And now I have to use the chain rule to differentiate these. Never forget that. Because while the cumulative, you could imagine this as the integral of the density up to square root y. But when the right limit of the integral is not y, but a function of y, you have to use the chain rule. So the chain rule here gives us 1 over 2 square root y. That's the derivative there times. Now, we all know that x is normal 0, 1, so it has density phi, which is the standard normal density, square root y. And then minus 1 over minus 2 square root y, phi of minus square root. Now, luckily, phi is an even function, so this all cleans up very nicely to equal phi of square root y divided by square root y, and I can even say explicitly 1 over square root 2 pi y e to the minus x squared, which is e to the minus y, square root y squared divided by 2. So that's the nice formula. And so much so, we recognize that as that is equal to constant times. I didn't care what the constant was. Y to the power minus a half, e to the minus y divided by 2. Now, straight away, you knew that meant that y has a distribution that is gamma. If you don't recognize the constant in the density, it doesn't matter so long as the others match. This is the density gamma. Alpha is positive 1/2 because that's alpha minus 1, and beta is 2. Okay, but that's also called chi squared 1. And that's because it's the same distribution as the square of one standard norm. And we even also talked about how if you put together lots of independent gammas, you add up the scale parameters. So chi squared d is gamma d over 2. We'll get to that in a moment. Okay, so that's an example we've already covered. It is hard if you can't. So this is once again method 1. CDF method is hard if you can't solve for g of x. You have this inequality g of x less than or equal to y, and you have to solve that in terms of x. In principle, to do this, you have to solve it in terms of x. So that's one of the main motivations why we want more methods, and so we're going to do another method now. So method 2, which will be called the derivative method. Maybe this is not the same nomenclature as the book, but it just goes based on the densities themselves. The statement of this is that if G, I want to be careful about stating this. Because there can be a little bit of so certainly y equals g of x, and x has density fx, and y is a value such that the key criterion is f prime of y is not 0 for g prime of x is not 0 for all x such that g of x equals y. So that's a funny criterion, and I'll illustrate it by means of a picture. The picture is if I do have my function g here. Now imagine that's the function of y equals g of a very standard xy plot of it. And then I take a particular cross-section. So I have a particular height, right? So that is the particular y value I'm interested in. It has certain x values. And you'll notice at each of those x values, the derivative is non-zero. There's a non-zero derivative at each of those x values. Then, what happens? Let us say this, the density of y, which I write f subscript y of y, is equal to sum over all, I'm summing over all these particular x, there might be 3 of them in this case, I'll just say x1, x2, x3, but I'm not assuming how many of them there are. In principle, you could have infinitely many if they added up to a finite derivative, but just imagine a finite list of x values that give you that particular y. So those 3 x values would actually be called the pre-image of y. So the pre-image doesn't have to be single one. If the sum over all x's such that g of x equals y, and then I have to add up the absolute values of the derivative, g, derivative of g at each of those x values. That is how much it scales by, and multiplied by each of those is taken to the power minus 1, so you take the reciprocal, and then you multiply that by the density f outside bracket. Fx of x. Okay? So that's a big complicated thing. Why is this true? It's true because what's the chance that y lies close to this y value? Well, to be within a little interval close to y, that means if you imagine that to be a small interval, you could be in any of those three segments, right? You could be here, or you could be here, or you could be here. And each of those has a probability of happening. It's the chance that x lies in a certain closer region, and that's given by the derivative. So I'll also say it can also be proved using method 1, but I think I'm not going to give the proof at this point. Let me give you the simple case of this. When G is bijective or just 1-to-1, f y of y, the density of y, well, it's 0 if y is not in the range of G, right? So, because y equals G of x, so if it's not G of something, then there's zero probability of getting something that's not G of x. And if y is in the range of G, then there'll be exactly one pre-image. And then that is just fx evaluated at that pre-image, G inverse of y, divided by the absolute value of G prime of G inverse of y. I'm replacing x with G inverse of y. So if you want, there's actually two ways of writing that. F y of y equal to, just to abbreviate, fx of G inverse of y divided by absolute G prime of G inverse of y. If you remember your chain rule, the G prime evaluated at G inverse is also related to of G inverse of y multiplied by absolute value of G inverse derivative evaluated at 1. So that's another way to say it. So all of those are seem like very complicated ways to say it. I wrote those because those are fully precise and include all the terms. I think probably a better way to remember this would be fy of y equals fx of x times the absolute value of dx dy. Okay, so that's in the kind of Leibniz notation, where y equals g of x and x equals g inverse of y. So that's probably an easier way to remember this. And let's, that can be derived from a number of ways. Essentially, if you're looking at even if you can't solve for these points exactly, you can express the cumulative distribution of function of y in terms of certain regions where x could be. X could be there on the left or in between those two. So let's do an example of that second case. Let's do x. In this case, I'm going to do a Cauchy distribution. I might have mentioned that in words before, but the density of a Cauchy distribution, this is one that actually doesn't have an expectation, is 1 over pi times 1 plus x squared for all real x's. Okay? And let's do, I'm going to do the same example as before just because it's easy. And let's not even do that. Let's do the cube of a quotient. So that's going to be even more extreme. This is bijective. Because it's bijective, we have the relationship x equals y to the power 1/3. And then dx by dy is easy to calculate here. It is 1/3 to the power minus 2/3. So f y of y is equal to fx of x. So I have to substitute in y to 1/3. 1 over